the disk method, our objective is we'll be able to write a definite integral that gives the volume of a solid of revolution that is obtained by revolving a region in the xy plane about a specified axis of revolution. Today we're going to look at a problem where we have a vertical axis of revolution, so we will be integrating with respect to y. And this is, of course, the integration formula for the disk method. This is a problem that we did yesterday, but we're going to change the axis of revolution. Yesterday, the axis of revolution was the horizontal line y is equal to 1. Today, we're going to change it so that the axis of revolution will be the vertical line x is equal to 0. We can also say the y-axis, because the vertical line x is equal to 0 is, in fact, the y-axis. So what we want to do is, right here, we want to write a definite integral for the volume of the solid of revolution obtained by revolving the given region about the given axis of revolution. When doing these problems, your first step is to sketch the given region, which has already been done. But if it weren't done, you would sketch it first. And then you're going to sketch a representative rectangle within the given region. And then you will sketch what you get when you revolve that rectangle about the axis of revolution. So let's start by looking at the region. We have the region in quadrant 1, bounded by the graphs of y is equal to negative x squared plus 5. Here we have the graph of y is equal to negative x squared plus 5. And y is equal to 1. So here we have the horizontal line y is equal to 1. And we know our region is in quadrant 1, so it's in the upper right quadrant. So the region in quadrant 1, bounded by the graphs of y is equal to negative x squared plus 5 and y is equal to 1. So here's our region. And we want to take this region and we want to revolve it about the y-axis. So here is our axis of revolution, the y-axis. So we will take our region and revolve it about the y-axis. And that will give us a solid of revolution. So our next step is to draw a representative rectangle within our region. So here is our representative rectangle. Within our region. And then we will revolve this rectangle about the axis of revolution, and when doing that, we obtain a cylinder or a disk. So here is our disk. So because we obtain a disk when we revolve our representative rectangle about our axis of revolution, we know we will be using the disk method. How is it that we should integrate with respect to y in this particular problem? How do we know that this is an integration with respect to y problem? The reason we know that is because when you look at the orientation of the disk, the height of the disk is over here. This is the height of the disk, and it is a height that can be found by subtracting two consecutive partition points, and we're partitioning the y interval from y is equal to 1 to y is equal to 5. From the bottom of our region to the top of our region, we go from y is equal to 1 to y is equal to 5. And that interval of y values from 1 to 5 is partitioned into a number of subintervals, and the width of each subinterval is given by delta y sub I, which of course will correspond to the height of a particular cylinder within our region. And because the height of a particular cylinder is given by delta y sub I, we integrate with respect to y. So the next two questions are, what about the limits of integration and the integrand? Well, the limits of integration are easy to figure out. You just go from the very bottom of your region, where y is equal to 1, to the top of your region, where y is equal to 5. So the very bottom of our region is here, where y is equal to 1, and the very top of our region is here, where y is equal to 5. So the limits of integration are from y is equal to 1 to y is equal to 5. So we just need the integrand. And if you look at this method, the integrand is going to be a function of y that will give us the radius of a particular cylinder. And once we have that function of y for the radius of a particular cylinder, we need to square it to get the integrand. And don't forget the constant factor of pi, which has been factored out from the integral. So how do we get our function of y for the radius of a particular cylinder? Let's go back to our cylinder that we had drawn earlier. So here's our cylinder. And where is the radius of this cylinder? I will use blue ink to show you where the radius is. It's right here. And right now I will go ahead and erase other parts of the diagram so we can just focus on the blue horizontal line segment, which is going to give us the radius of a particular cylinder. So here is our horizontal line segment, and we need to find the length of this horizontal line segment because this horizontal line segment is going to represent the radius of a particular cylinder. So now how do you find the length of a horizontal line segment? As we learned a couple of days ago, you need to subtract the x coordinates of the right and the left endpoints. So the right endpoint is on the graph of y is equal to negative x squared plus 5. So this will have coordinates x comma y. But we want to write x as a function of y. We want to write x in terms of y. And the reason for that is because our integrand has to be a function of y. And to find the length of a horizontal line segment, we have to subtract the x coordinates of the right and the left endpoints. It's much easier to do that for the other endpoint because the other endpoint is on the vertical line x is equal to 0. It's on the y-axis, which is of course the vertical line x is equal to 0. So I will simply assign these coordinates to the left endpoint. X I can just replace with 0 because no matter where I am on the y-axis, x is always 0. Regardless of the y coordinate, x will always be 0 because I have a point on the y-axis. So we just have to figure out how to write x in terms of y for the x coordinate of the right endpoint. So here's what we need to do. We know that this right endpoint is on the graph of y is equal to negative x squared plus 5. So we're going to take that equation, y is equal to negative x squared plus 5, and we're going to solve this equation for x so that we will have x in terms of y. So we can begin by adding x squared to both sides of the equation. So when we do that, we get x squared plus y is equal to 5. And then we can subtract y from both sides of the equation. So we get x squared is equal to 5 minus y. And then we can take the positive square root to get x is equal to the positive square root of 5 minus y. You might be thinking, Why is it that we're taking the positive square root? Because we're looking at the part of this graph that is in quadrant 1, and in quadrant 1, x coordinates are positive, and that is why we take the positive square root rather than the negative square root. So that allows us to replace the x coordinate with the square root of 5 minus y. So any point that's on the graph of y is equal to negative x squared plus 5, you can replace the x coordinate with the square root of 5 minus y. We just have x written in terms of y. We need to do that because having done that, we can now subtract the x coordinates of the right and the left endpoints of this vertical line segment to get the length of this. I said vertical line segment, I meant to say horizontal line segment. To get the length of this horizontal line segment, subtract the x coordinates of the right and the left endpoints. So r of y, the radius as a function of y, is the difference in the x coordinates of the right and the left endpoints. So this is what we have. R of y is equal to the positive square root of 5 minus y minus 0. So when you simplify, you just get the square root of 5 minus y. So I have a function of y that gives me the radius of a particular disk within my solid of revolution. And it's a function of y because the disk could be anywhere within our solid of revolution. It could be closer to the bottom, in which case the y values will be closer to 1. It could be closer to the top, in which case the y values will be closer to 5. So that is r of y. And with r of y, you can write the integrand. What is it that you have to do to get the integrand? You take r of y and you have to square it, because that's what the disk method says you should do. So now our definite integral that will give the volume of this solid of revolution is, volume is equal to pi times the definite integral. The limits of integration are from y is equal to 1 to y is equal to 5. And the integrand is going to be r of y squared. So r of y is the square root of 5 minus y, and then I have to square it. And then we have, of course, we're integrating with respect to y. You can simplify because the square of the square root, the squaring and the square rooting are inverse operations. So when you simplify, you will just have 5 minus y for the integrand. So today we looked at an example where we took a region in the xy plane and revolved it about a vertical axis of revolution. This was an example for which we were able to apply the disk method to write a definite integral that would give us the volume of that solid of revolution.